Hello. Let's see how we could solve one of the challenges from Hitcon CTF 2019 using Ghidra. The challenge was named Core Dump and it was worth 242 points, and we get a description. Damn it, my flag checker, it's so buggy it destroyed the program itself. All I left is a core dump file. Could you help me recover the flag? And there is a hint that was available later during the competition. But yeah, we started with this core dump file. And of course, what we can do in such situation, we can actually check if the file is core dump, or at least if the file command reports this as a core file, and it does. The file is from home CTF flag checker. So okay, so more or less we know that we will be dealing with core dump file. And during the competition I solved this with one of the team members disconnected, and I will show you how we did it. It probably will be lengthy video, so maybe I will split it into two, but we'll see how it goes during the recording. Okay, so I got the file downloaded. I have here with a lot of other files that we will explain during the video, but let's just start Ghidra, and we will start analyzing the file to understand what's going on and how we can get the flag. Okay, so let's just import the file. We will import the file from Hitcon, core dump, and we have the core dump. And Ghidra analyze the file. Okay, recognize the format. We can hit OK. And yeah, of course the window is too big, we need to shrink it down, and we can open the file, release the dragon to start analyzing it. Okay, and first we'll start with the automatic analysis. Even though it's a core dump file, there's not proper headers as there would be in ELF file, but there is some structure, and Ghidra can analyze the file and recognize some parts of it as code and some of as like some data, and it's still being analyzed. But I guess we can already jump to strings, and we can see, okay, there is some strings that we could see. Please enter the flag, congrats. But if we go to those files, there is no reference, so we don't know where it's being referenced. But we can start from another angle. So let's just go to the function and see what Ghidra analyzed and what function we found. There are some functions from this 555 range, and we'll start with those. And actually we can see there's quite a lot of them. We could go one by one, checking the compilation of the function. There's not much in some of them, but if we go through all of them, we will see that actually the last one from this group, it's quite interesting. It's also quite big. If we scroll down, we can also see those strings, please enter flag and congrats. So we may safely assume that this is our starting function. At least it would be nice to start analysis from this function. And of course we can go from top, but we can also like jump in the middle, because if we see usage like this, okay, we have a function, we have some string that's being passed, and inside there's like a call to some kernel space. We can assume that, okay, this is some kind of puts function that it will print this string. And it doesn't matter whether it's puts or if it's printf being used. It's just for us to know, okay, here we'll be printing some information, and whenever there's like please enter the flag, the next would be function would be to actually get the flag. So we can also like rename it to f printf or whatever. It doesn't matter, just so we know that, okay, this is the place where we get the flag. And we can also assume that, okay, that this variable will hold the flag, and the flag will be at most 37 hexadecimal characters. Okay, we can also see that, okay, flag is also, the address of the flag is assigned to this local variable 140, and there is some checks here to see if we have like a new line entered, and then if there is a new line, we'll cut at the new line. So we'll just shrink a little bit if we got the new lines also with the flag, but it doesn't matter really for here. Okay, the next function we can see is, again, we are passing the flag to some function, we get a result, and then we compare with some like value which is close to this limit. So we can assume that this is checking the length of the string. So we can also rename it, and I guess this will be fail. This will fail the code. We don't know what it actually being done here, but we can assume, okay, the flag should have so many characters, and if it's not the amount we know it should be, we should just fail. So we can just, like, at least for now, rename it to fail. Okay, and then we can see a bunch of functions that being called, and then we have a printing message of congrats, the flag is Hitcon, and we print the flag. So we can also assume, and I know there's like a lot of assumption, but like it's usually like that. So you assume something and then you check if the assumption was correct, and if not, then you assume something else. But we can assume that those functions are being actually validating the flag, or somehow converting the string that we entered to see if we actually entered the right flag. And it looks like there's a lot of function being executed, so we might feel a bit scary to analyze them. But if we actually look a little bit closer to those functions, we can see that there's some kind of repeated pattern. So we have those three functions, 48BC, there's 4837, 49OF. If we take another three, it kind of looks similar. We have 48BC, the middle function is a bit different, but the third one is also 49OF. So again, yeah, we can see some pattern that we have like a one function as a like a header function, then the main function, and we do some cleanup maybe afterwards. And again here, and again here, and again here. And for the last one, we don't have the third function. We don't have the third function called, but we have also the two first. Okay, so it's not that scary. It looks like we have like a 5 times repeated pattern of function calls. So let's just analyze them one by one. And maybe before we do that, let's just see what parameters are being passed to the first one. So we have some kind of local 98. Let's just quickly see. Okay, local 98 is set to 0 here, and it's like some undefined 8 for now, so Ghidra didn't understand what it is. We pass a flag, we pass 10, and we, again, at least Ghidra identified that we pass flag twice. Okay, so let's just go to this function and let's see what's going on inside. So in here, we have only 3 arguments being passed, so maybe there's something wrong in the calling code, but for now we'll just focus here. And we can already identify, okay, we have a while, and we have some local variable which we can rename to I. So we just press L and rename to I. This is like a loop counter. And then we have a param3 which actually limits how many how many times this code will be executed. So we can also rename this as a count. Okay, so we already know a little bit more. So now what's going on here? So we have this local 28 and local 10 that we assign value from local 28 to local 10. And if we look here, this local 10 and local 28 is just like a local variables that are being used instead of those parameters that are being passed to the method. So if we look at this, it's just like a mem copy. So we can rename this function as mem copy. Actually, it will be mem n copy because we pass this count. so it's not copying till it gets 0. It will copy only that amount of bytes. Okay, so we know it's a mem copy. We can also clean a little bit this, so we know it's no longer undefined. I mean, we could just like assume, okay, we'll be copying bytes, so we can press Ctrl L and change the type of this variable, param1, and yeah, change already for param2. What we can also do, we can also change that this is our destination and this is our source place. Okay, so we have like a destination and source, and also we can rename those as like underscore source and underscore destination. Okay, so now it's a bit more clearer. We could actually maybe try, instead of a pointer, we could see if it will work if we'll just use like a byte array. No, okay, it doesn't work with that. So okay, so let's just go with a pointer. I was just thinking that maybe Ghidra will actually replace this with like actual array notation, but still this is quite readable right now as it is. Okay, so this is memcopy, so we can save and we can go back to our calling code. And okay, so now it actually changed. We no longer have 4, we have just 3 arguments, and we have this problem with casting to byte, this local 98, because local 98 is this undefined 8. And I guess we could probably rename it, but we would have to know what type it is. So we know that the flag is like a byte. At least, do we know it? Is it byte? We don't know. I don't know whether we changed. No, we didn't change the undefined type. So let's change the type of this flag. So again, press Ctrl L and we will get the data type chooser dialog. And here I will just use character, and we have a limit, hard limit, how many characters we want to read. So I'll just use character with a limit. And we got that, okay, flag is this 55 characters. We got some strange notation here. It's basically Ghidra, yeah, tells us that, okay, in this I will just clear from 0 to 7th values of this flag, because it's an array, so it will just do in multiple, I guess, moves. But okay, with that, I guess we could also somehow know that local also has to be this byte array, and we could also change the type of local. I'm not sure if we know how many bytes it will have, but I guess it has to have at least what? Here we will copy 10. Here will be 8, 12, 12 hexadecimal, so 18. See, okay, we don't know actually how big it could be. Not that big, the buffer, so I'll not change it now. Maybe later we'll yeah, find out how big the buffer is. But what we can do, we can again rename and call it buff, some kind of buffer, so it's a bit more clear. It's not longer local. Okay, before we jump into the main function, or actually the 2 main function, let's just analyze the last one from this triple calls. So 49OF. And if we go here, again, maybe before we go, okay, we are passing the buffer and we are passing the length, or well, some value. I already know it's a length, but we are passing some value. So maybe this will give us how big the buffer is. But okay, and again, we have this param2, it's being used in the while, so we can rename it to count. Ghidra identified this as being long, but we already know that, okay, buffer cannot be long, it will be byte. So we can convert the type, again, Ctrl L with byte pointer. And we already see that Ghidra here corrects this expression to param1 local c equals 0. So, and again, local c is just like a loop identifier. We can rename it to I, and param1 would be some kind of memory location. So this function is clear that it's like zeroing memory, some mem clear, we can name it. Okay, and it's quite clear with this notation. Okay, we get some memory and the length of how many bytes we want to store at this memory location, and we just clear it with 0. Okay, and this actually give us that, okay, the buffer should be also like 37 hexadecimal characters. So we can go back to our buffer. Where do we have the buffer? Let's just highlight buffer, and buff is set to 0 here, and it's here. So again, Control L, and let's just use it, byte 37, and we have a buffer for our code. Oh, actually, flag will be copied to this buffer. And again, we got rid of this byte casting, which is good. So now it's a bit more clear what's being done here. So, okay, memcopy copies parts of the flag to the buffer. Then we do something with, too many clicks, sorry. So we copy flag to the buffer. The buffer is passed to this method, which we don't know yet what's being done there. And then we clear the buffer. And then again, we copy some other characters from the flag. So I guess here it will be from 10th. So 8 characters from 10th to the buffer. And then it will be passed to this function and clear, and so on and so on. So basically, as we can see, in those methods, we are actually, each of this function is checking part of the flag. Okay, so now we actually need to find out what this function is doing and what are those already yet unknown locals are being, what is stored there and how it's being used in this function. So maybe let's first go into the function and try to see what's going on here. And it's a bit longer than the previous one, but it's not that long. So this is basically just like a stack canary being set, and here it's being checked. So that's not that important. What we can see here, a while again, we can rename to I. It will be a bit clearer. Okay, so we check if I is not equal to 0, and then we set a value 0 to some local address, which is from this local 518, which is like an array of 161 bytes. So this is just like a clearing memory, which will be used here. So let's just like call it some kind of memory, and we can also change the type. We already know it's not undefined. We can change it to byte of 161. Okay, and also this pu var2, we can also change it to byte pointer. Okay. We got some problems here, but yeah, I mean, it doesn't. We can actually maybe revert this change. It doesn't matter that much. We already understand what's going on here, so maybe it doesn't matter to change it. Thankfully, Ghidra has undo, so Control Z and you can undo. Okay, what's going on further? So those lines are actually quite interesting because we are passing those parameters that are being passed to this method along with the memory that we just know that we clear here. And then we don't know what this function is doing, but then when it returns, we actually should be able to call this memory location. with some more parameters. So we know that, okay, we cleared the memory here, so there will be all zeros. So somehow this method will fill this memory with bytes that actually are some valid code, because I guess, at least in theory, this code should work. We don't know, maybe it break here, but at least in theory it should work, because we already identified that, okay, this method should validate somehow if the flag is correct. And we can see that, okay, we are calling the memory, we get some result, we can rename as result, and if the result is 0, we call this failed method. So I guess if it's again, if our assumption was valid and it will fail, then yeah, if the flag will be invalid, then yeah, it's a bit strange that the 0 is failed, but maybe, we don't know. For now we don't care. It's just, let's just analyze more of this method. So let's just jump into 4963. We know that the third parameter is this memory location. And yeah, so actually in here it looks like we have only 3. Again, some problems in Ghidra, but we again see some interesting stuff because we see XOR operation. So whenever you see XOR, it's interesting because probably something will be decrypted with a key. But okay, so we know param3 is our destination buffer, so let's just rename it. And okay, first the type, we know it's no long, it's like a byte pointer, so let's just use that. And we know that, okay, it's destination. Here we'll be setting the value. Okay, and local 1 is we can see it's assigned to 0 and it's incremented every loop, so we can again safely call it I. So we already see, okay, destination of this I element is based on param1. So param1 plus I, again, it's not long, it will be again byte pointer. We can assume that. It would be very strange if it wouldn't be, but we can of course verify, and it would be I guess source. So yeah, if we have a destination, if we have a source and we have XOR, then what we are missing is the key. So param2, we can assume, would be the key. We don't know the type of this key. It could be a number. There's some kind of strange, maybe not strange, but a bit more complex operation going on than just getting the element from this. So it might not be just like a byte array, but we don't know. But still, we know a little bit more. Okay, there is some decryption going on, so we can call it XOR decrypt. Okay, so maybe let's just go a little bit back and try to find out where this source and key is being passed from. So we know it's being passed as parameter 1 and parameter 2 from this method. So okay, so let's just rename. So param1 would be our encrypted data, because we will be decrypting it, and param2 would be the key. Okay, and we can see that there's param3 and param4 which are being passed to this decrypted code, as we can see here. But for now, okay, we know it should not be date, it should be encrypted data. So we know, okay, first and the second parameter passed to this method is encrypted data and key. And we also know a little bit how we could call this function. So what it does, it's decrypt, run, and that's all. So maybe let's just call it like that, decrypt and run. Okay, so we know a little bit more. So now, okay, let's look at encrypted data and key, how they are being passed to this method. Okay, let's just go to our calling side. So this is this local 128 and local 120. So let's just see what this local 128. So we can see it's being here, and it's just keeping a pointer to some data. And the data, if we go here, actually looks like it might be some encrypted data. There's like a random stuff that looks like random, and there's a lot of that. So it's not very short array, it's quite big, but also we can see that, okay, there is some pattern here. We have 128, 118, 108, F8 and E8. So we can see like 10 hexadecimal difference between those addresses. And we are assigning some data here, some data here, some data here, some data here, and some data here. So it looks kind of interesting. And also interesting is this code, as it's also very nearby. So it's like local 130, but it's also using some kind of offset addressing. So it might be that those are connected. So let's just clean up and try to understand if we can reason what's being done here. So I would first start with renaming those data. So let's just call it encrypted data 1. So we know what's here. Encrypted data 2. Okay. Encrypted data 3. Data 4, and encrypted data. There's no mystery here. Okay, so we have those encrypted data, and we can, again, while with a variable, call it I or J, whatever you want, just short name. Okay, and you can also see like local 130 here. We also assigned something similar like this. But there's some kind of like zeros, so something is missing here, but it looks similar. And it's also interesting here that there's like those addresses are not like 8 bytes to each other. They are not aligned. There's like 16 bytes between them, so there might be indication that there is some kind of structure. So it's not only pointers, but it might be some kind of structure. And what we can do in Ghidra, there's like auto create structure, we can call it, and Ghidra will create some kind of a struct basic structure for us that we can of course modify now. So basically now there is no no structure of this structure. So let's just add one field, and we'll data type will be we just need the pointer int, but it should be, I guess, 8 bytes. So maybe let's just use like a DQ. There's no DQ here. Okay, let's just use long for now. It doesn't matter. We just need something, okay, long for now. We'll change it later, and let's call it D, like data. Okay, so we have our structure a little bit, but also from this while loop, we can think of that there will be, actually I did the wrong thing, because I should not create structure on this one. I should create a structure on this one. Maybe it did correctly. Okay, we'll see in a moment. So also from this loop, we can see that we'll have more of those structures. So it's like basically it will be 5 because we have those 5 datas with something else. So let's just go to the most higher addresses, which is this 130, and we can see that Ghidra, okay, it actually tries to analyze and it sees, okay, there might be like 2 elements, but we know that it's not correct. So let's just change the type, and we will use this a struct which we need to actually change the name quickly, and let's just give it a 5 items. Okay, and a struct. So so we can see, okay, in some places it actually analyzed correctly that there is like something being assigned, but when we see those like underscores and digits, we can see that there's like alignment is not really correct. And also here it says like, okay, like index 1 then index 3, but there were like almost like there was like 16 bytes offset. So we need to update our data type. So let's just search it for a struct, and let's just a little bit modify it. So first let's just give it a proper name, or maybe a bit proper name. So let's just call it encrypted data. So we need 16 bytes. So let's just for now, just so we don't have like bytes, let's just it doesn't fit. Okay, this is like when you define a structure and you already have a field, you need to do like move it down. Now we'll change the type to int, so we'll have 4 bytes. Let's call it A, and now we'll move it up. It's like a bit stupid, but okay, not the one. So we'll do the same with this one. So we'll just use int, we'll call it B. We don't know what's there, but and we have 4 bytes. So we have in total 16 bytes, and this is what exactly we wanted from this structure, because we saw that there is like a 10 hexadecimal bytes difference between those assignments to the data. If we do that, it actually broke everything, because we'll need to redefine this variable, because for some reason Ghidra thought it will just break whatever we did before. So again, encrypted data and 5 elements in array. Okay, so now it looks actually a bit more clear. We can see that all those locals were folded into this encrypted data, and we can now see that, okay, it's actually very nicely aligned, assigning to this D those encrypted data. So maybe the D should be called encrypted data, because it looks like this is what is being assigned there. So let's just rename it encrypted data, maybe with like a proper casing. I don't know, it's not that matter. And this long is still being cast, so maybe we should get rid of this. Let's just maybe keep for now long. I just wanted something that's 8 bytes. But let's actually see what's being used. It's used keyword, move keyword. Okay, so there should be some other type it's more suitable. DQ, we don't have DQ. Do we have like an int pointer that it should be 8? No, and maybe long pointer. It's still like 4 bytes. Okay, let's just keep it long. It doesn't really matter. We'll just have to deal with this casting, but it doesn't matter for us. Okay, so we have pretty nice alignment here, but okay, here also it's a pretty nice alignment that we can see, okay, we are assigning something to A and B. So let's maybe see what's in those addresses. So here, if we look, and it's just, we go every fourth byte. So we can actually, we can use Ghidra's data command to, we want to have a D word, and then we can press Y to do the same operation again and again. We can see actually we have a 5 D words here. And I hope you already can guess what are those, because again, we are guessing, but my guess was that those are the keys. So we can rename this as keys. So we have a keys array. So A actually would be in our encrypted data, would be a place where we store a key. Okay, so we have that. Yes, save changes. Okay, so we have a key. So what's B now? So let's again go here and see what we have. Okay, so it's like 10B. Okay, we don't know what it might be, but again, let's just convert to D word, because again, we jumping every 4th byte. Okay, 1B1, 2A4, 386, BF. So there are quite a small numbers, and again, we could actually go and check, but we can also assume, okay, those might be actually the length of the encrypted data that we have in here. And again, that would be a good assumption because this is actually what's here. So encrypted data sizes. And here, and B should be called in our encrypted data length or size. Okay, cancel, save, and close. Okay, so we now know, okay, we have key, size, and encrypted data, and this local 130 could be renamed to, I don't know, yeah, naming is hard, so maybe end data. Not the perfect name, not the worst name. Okay, so we can see, okay, from end encrypted data 0, we pass this encrypted data 1. Well, I use 1 indexing. Here it's of course 0 indexing. 2, 3, 4, 5, we assign key and size. But we can also spot something that there is no key and size for 0. So we start from 1. And this is being done here. But if we go here, okay, the key is null. The size, there is like 11 hexadecimal, but we don't have a key. Maybe we'll have to deal with that. Maybe it's not needed. We don't know. But at least now, after all this talking of me, we know where the data is coming from. So the first argument, the encrypted data, is actually encrypted data from index 0. But the key is actually from index 1 with this strange notation. And this strange notation is actually that, okay, our key and size are 4 bytes each. And here it's being passed as like 8 bytes, something that of size 8. And actually we could fix that because probably, I don't know, I haven't seen it, probably the encrypted data is a bit different. So it's not, we don't have those two data types here, but we have like a additional data type that contains those two types, like a header and encrypted data. And we could do that. I hope Ghidra will not destroy everything what's done here, but let's just try. So let's just create a new structure. Let's call it a header. Let's give it 2 ints. One would be key. I already forgot the order, but I think that's correct. And okay, and the second one, okay, again, I need to move it down. It's really annoying. Size. Was that the order? I don't remember. Let's just see. So first was key, then the size. Okay, key size. Okay. Okay, so we have this new structure, and then we'll just use it in this one. So let's just remove those two. Let's just add a new one, which of type header. And again, yeah, I cannot fit it in 1 byte. I need to move it down. Type of header, and let's give it like H name. And again, let's please not break everything. Yeah, something not right, because here it actually assigned to, okay, I forgot to move it around. So it has to be like this. So header, then encrypted data. And let's just see. Okay, encrypted data is nice. Here it's H key, H size. And if we scroll down, yeah. So here correctly passing the header as a second argument. So actually we identified a bit wrong. This is not a key. This is of type header. So we can also again change the type. And it's header. And now if we have like that, if we go to this XOR decrypt, this is actually also here we can rename everything to have a clear picture. Again, it's H, and we can now know, at least we can understand what's being done here, because actually it's here we are passing like an 8 bytes, and this is like extracting the size of the data. So this is like length, and here it's extracting the key. And from this one, this key is not uint. Well, it could be uint, but this is basically we are extracting each bytes from this key. So that's why we can see this strange structure here. It's basically take one byte, then the other, next and next, and use it for XORing the source bytes. So basically, yeah, if we look at the key are 4 bytes. And of course, we need to extract each of those bytes to what? To decrypt the code. Okay, if we go to the keys, we have those bytes, and we need to extract 4A, O3, B5, E8, and use them over and over to decrypt the encrypted data. So for this data, we'll use this key, and for this data, we'll use the next one, and so on and so on. Okay, so actually we know quite a lot now. What we don't know is this function. But if we go to this function, actually it's very similar. We can see our XOR decrypt, we can see our clearing the local array. So it's actually the same. The only difference is that here we are just passing one parameter, and in the other one we're passing more. I don't remember it. I think it was 3. So actually we don't need to analyze it maybe later, but we can rename it decrypt and run, just so it's a bit different. Let's add a suffix 2. Okay, so actually, yeah, we know quite a bit. So now I think is the time to actually extract the data and decrypt it. And this is actually what my script does. So this is the data from Ghidra. I think I will just like copy paste it from Ghidra. Of course, you could just open the file and navigate to correct offsets. But yeah, at least at the moment it was easier. We have the keys in the reversed order, so 4A, O3, B5, 8E, and we have a Pursman decryption. I guess it could be done a bit nicer, but nonetheless it does the job. So after we run it, we'll get 5 parts decrypted. So each part will correspond to each of the data decrypted from the correct key, and in those parts we'll actually find the algorithm that validates the flag, checks that the flag is correct, and I guess we'll stop here and we'll deal with the parts in the next video, where we will do more or less the same as in this one, but we'll focus on just those 5 parts of algorithm validating the flag. So that's all for this one. I hope you learned something, and if you did, please like the video and subscribe. And yeah, see you next time when we will analyze parts 1 to 4 or 0 to if you can count from 0. But yeah, so that's all for now. Bye.